How much can one building impact a city? Well, I made a simulation to explore this question. That probably made no sense, so let me explain how I got to this point. Imagine a new city is being built on empty land. To keep things simple, the city will only have three types of buildings. Residential buildings where people live, these are blue. Industrial buildings where people work, these are orange. And recreational buildings where people enjoy themselves, these are green. The empty land is split into a grid. In each square, the city will build one of the three building colors. Each square has a number that represents how suitable it is to build each color on it. This number is on a scale from 0 to 1, so a square could have a suitability of 0.9 for blue buildings, 0.5 for orange buildings, and 0.1 for green buildings. This would be a good square to build blue buildings, an okay one to build orange buildings, and a bad one to build green buildings. The suitability values for each square and each color are completely random throughout the grid. There's no patterns or correlations. The simulation starts with an empty grid. The city's first building is blue, and it's built on a random square. Next, an orange building is built. Its location is on the square with the largest orange suitability that's adjacent to the blue square. In this case, this is the 0.30 square. Next, a green building is built. Its location is the square with the largest green suitability that's adjacent to either of the existing buildings. In this case, this is the 0.85 square. The city needs an equal proportion of each building color. So in the order blue, then orange, then green, squares are filled until there's no empty squares left in the city. At the top, you'll notice a number that's increasing. That number is the sum of all the suitabilities of all the squares that have been built on. At the end of the simulation, a larger number means a better city. To check if you understand everything, pause and try to predict what square will be built on for each iteration. This is pretty simple, but you need to understand this to understand the rest of the video. A key part of this simulation is that the first building is built on a random square. Since all buildings are built near existing ones, the starting position of the first building has a snowball effect. By changing the starting position, we can see how much of an impact a single building can have on the city. Let's move on to the actual simulations. In the top right is the city grid at the end of a simulation. These three grids indicate the suitability for each color. Remember that squares with darker colors have higher suitabilities. To the right is a graph that shows how the city's total suitability changes over time. Each colored line indicates the total suitability for all the buildings of that color. I'll run through some simulations now. Note that the red square in the city grid is the starting position of the first building. And now, to make things faster, I'll just show the end results for every starting position. Now, I've isolated the two cities with the smallest and largest total suitabilities at the end of the simulation. At the top is the smallest with a total suitability of 46.6, and at the bottom is the largest with a total of 49.6. Keep in mind that the only difference between these two simulations is the starting position. Everything else is the same. The total suitabilities don't mean much on their own, but by dividing the smaller number by the larger one, you get a ratio. In this case, the worst starting position was 94.5% as good as the best starting position, a number I'll call the relative suitability. But this 94.5% similarity is only for that specific city and its specific random suitability grids. Now I'll simulate 100 more random cities with random suitabilities to see how different their best and worst starting positions are. The city grid on the left has the smallest total suitability for a given simulation, and the one on the right has the largest. At the bottom is a graph showing the count of the relative suitabilities from all of the simulations. After 100 simulations, relative suitabilities around 95 to 97% are the most common, with the biggest difference being 92% in one simulation. This is a look at the 92% one. Interestingly, the starting positions are quite close to each other. Looking at the graphs on the right, I noticed the bottom city had a larger suitability throughout the entire simulation. The relative suitability rose from around 80% at the start to 92% at the end. I think this rises because when a city is young, it has fewer neighboring squares than when it's older. Fewer neighboring squares means less choice of where to build, and thus a larger probability of building on bad squares. Related to this point, the simulation on top has a starting position on the edge and near the corner of the city grid. From the very beginning, it had fewer neighboring squares to expand to compared to the bottom simulation. Now, I'm going to add a new dimension to the city grid. Imagine there's a river flowing through the middle of the city. This river would make it hard for one side of the city to access the other. I'll model this by introducing a border. The border consists of squares that are part of the city but can't be built on. These squares will be black. To generate a border, the first square is randomly placed on the edge of the grid, excluding the corners. Each iteration, it can move forward, left, or right until the border reaches the other end of the grid. The possible next squares are highlighted in red. Now, squares are randomly removed until there's a connection from one side of the border to the other. Take a second and try to predict what impact adding a border could have on the simulation. Now I'll show 100 simulations of cities with borders. Once again, on the left will be the city with the smallest total suitability, and on the right will be the one with the largest. This distribution can be compared with the previous one from the 100 simulations without borders. From this, we can see that when there's a border, relative suitability generally drops, and there's a much wider range of results. I think this is primarily caused by the border limiting the amount of squares that can be built on as the city grows. Again, let's look at the biggest difference between simulations. Here, the two starting positions are on different sides of the border, and midway through the simulation, the difference between the city suitabilities isn't too notable. However, at this point, the city on top has not reached the left side of the border, while it has almost filled out the right side. The square at the bottleneck of the border has a low suitability for all three colors. So the city won't expand to the left, meaning there's a limited amount of squares it can build on. When it finally reaches the left side of the border, there's usually only one possible square to expand to, and the pattern of building blue, then orange, then green buildings must be followed. By chance, this pattern leads to building on a lot of low suitability squares. Comparing the left side of the border between the two simulations, the bottom one is much darker than the top. I quite like this example because it shows the potential impact of a border, and it reveals that small details of a model, in this case the building order of the colors, can also be impactful. Now I'll make one final modification to the suitability grids. Rather than each square being completely random, the squares will be grouped in batches. Batches are groups of adjacent squares which all have the same random suitability. In this example, there will be 8 squares per batch. To start, a random square will be chosen. Each iteration, the batch will randomly expand to one of the adjacent squares. These are highlighted in gray. The batch is complete once it reaches 8 squares. Then, a new random square is chosen and the next batch is formed. In the case of these yellow squares, there's not enough room to reach a total of 8, so the batch is complete when there's no more room to expand. Once all the possible squares are in a batch, a random suitability value is given to each batch. All the colors share the same batch squares, but they're given different suitabilities. For example, here are the suitability grids for blue, orange, and green batches. Once again, this is the relative suitability distribution from 100 simulations. Note that these simulations have a batch size of 10, and the border is still included. Compared to the two previous distributions, adding batches significantly lowered the minimum relative suitability. One last time, this is the biggest difference between simulations. The bottom simulation's starting position is in the middle of the border. It was able to expand to the good squares on both sides of the border simultaneously. But the simulation on top was stuck on the right side of the border at first, and there it built suboptimal orange and blue buildings on squares that were good for green. Then, when it reached the left side of the border, the city was building suboptimal green buildings in squares that were good for blue and orange ones. So, the combination of borders and batches has the potential to lead to bigger differences in cities than just a border can. So, can one building significantly impact the future of a city? Well, yes, at least in the realms of this model. We saw large impacts due to one building when comparing the best and worst simulations. In general, there is a greater impact when options for building new buildings were limited. This was seen when starting positions were near edges, borders, or far from other batches. We also saw that small details of the simulation, like the building order of the colors, can have big impacts, even if these small details seem inconsequential. To me, this feels like a parallel to real-life zoning laws, whose minor details can lead to unintentional outcomes. However, these observations can be thought of as being dependent on the model. The model I created is really simple. Perhaps a smarter one could do a better job at picking the best squares to build on, and that in turn would limit the impact a single building could have. But maybe that smarter model would have its own unique quirks that allow one building to impact the city in different ways than we've seen. If we step back and think about the real world, how much could one building impact the future of a city? Well, based on what I learned from this, I'd say it could vary a lot depending both on the city's environment and who's planning the city.